Hello and welcome back. In this video, we will look at the kind of transformations that are typically used in the context of rigid registration techniques. So, the first transform, the most simplest transform, and it is typically a part of all rigid transformation registrations. We will look at so-called translational transform, right? So, we will represent that by this vector v, which has to be applied to every point in the physical coordinate space in order to map it to an output. Okay, so I've written it in the form of the vector because the idea is that if x prime and x both have a certain number of dimensions depending on the image. So for instance, if the 2D image, x prime will be two-dimensional. If 3D image, x prime will be three-dimensional. So if we write it in its more general form, then we will have x1 prime up to xn prime for an n-dimensional image. It's equal to x1 to xn plus 1 to n. Right. So this is the most general form in which you can write this. This transformation is typically very easily managed especially for rigid body registration, and it's always the first thing you would try out when you're trying to register two different images. Okay, so it's a fairly simple enough transform. Once again, remember all these transformations are applied in the physical coordinate space and not on the pixel space. So you'll have to convert from pixel index to this x, which is your in millimeters, and then of course this v1, v2 up to vn, depend on the for each dimension there is one translation. So you would apply this translation to every pixel in the picture in order to get the output coordinates. Okay. So this is the most simple transform that you would do in the context of medical image registration. The second transform, which is slightly more complicated than the first one, is a scaling transform. Now, here there are different versions of it. So the one we have shown here is wherein you are applying the same scaling. This is basically the scalar that you apply to all the dimensions of the image. Okay. There is also this anisotropic scaling where each dimension will get a slightly different scaling factor, and it is much more complicated. This is also difficult to optimize because this is multiplicative and it has non-linear effects. It also depends on the origin of your coordinate. So for instance, if the origin of the coordinates is in the center of the image, then it will have like a magnification effect, right? So, but on the other hand, it's basically because it's like radiating in all directions. That kind of effect is what you get. But if your origin of coordinates is in the top left, or so let's say bottom left, then it has slightly different effect. Appearance differs, depending on the origin, slightly different effects can be obtained. So you have to be careful about using this transformation. Typically it's used when you really don't know the scaling factor involved, maybe during the image acquisition process. The images could be acquired with slightly different dimensions, different magnification. So that problem is there. So to address that problem, you can use this scaling factor. Once again, the most simplest application is when you are using it using a single scaling factor across all the dimensions. And if you write it in the form we did for the translation, so for across every dimension, where n is the dimension of the image, you have a unique, you have the same scaling. So you do the same. So here D acts as a scalar. Okay. So the other transformation that you typically is overlooked, and I think is much more important, let me take off the annotations here, is the image center. Now this becomes very important when you are doing rotation. So typically what you assume is that you are assuming that when you do rotations in an image, which is again part of a rigid transformation model, you assume that it's usually done through an axis through the center of the image, right? But that's need not be the case. Sometimes you can also apply rotations with the origin fixed at the bottom left corner of the image. So that way, this knowing the center becomes important. So typically, you would not estimate this as part of the registration process, but rather you would just fix the center, right? So then before you apply the scaling transform, you would move the center, move the origin to the center, and then do the scaling, and then move back before you do the translation. So for instance, this particular expression I've written here, it would translate to the following. So across the dimensions of the image, you have your scaling, but you apply after you move plus, and then on top of that you can also have the translations. So just of course you have to reset every time you do this. So you have to move the origin, that is fixed. When it says move the origin, it means that depending on when you want, where you want to, with where the origin should be when you do the scaling or the rotations, you do the following operations. So there are software packages which readily implement this. So even in them, you would ideally, fix this. This is not estimated. You would fix it, and after fixing it, you would do the translations and rotations. Okay, so the next thing is the 2D rotations. Once again, for any rigid body transformation, it's not complete without this. So here the expression would be, for instance, if you're working in 2D space, typically, hold on for a second, and seem to have moved it. So for instance, you would have, in this case, your x prime is basically prime y prime. Then you have your rotation matrix. We saw this earlier also. And then you have, because once again you would move your coordinates, origin of coordinates, and then of course add them back after you do the rotation. You also have the option to add translations following all this, right? You can also add, after your rotations, you can translate, right? So this is a typical setup. You do similar things if you want to do this for 3D. Once again, you have to fix the axis, and based on that, you would move them. Fix the axis in the sense, the axis of rotation, whether it passes through the center of the image or through one of the corners. Then you would affect your rotations, and then of course, if there are any other transformations, like for instance, in the case of rigid body translation, you typically end up doing a translation, right? So I mean, there are different ways of representing this. There are there's versors, etc., which represent these kind of transformations. Not go into such details, but typically to understand the parameters involved in all of these translations here. This is minus, if you missed it out. Okay. So, but some of this stuff is, you must have seen in some of the linear algebra courses or in some other course, maybe another medical imaging course. Fairly straightforward, but coding this appropriately, applying this correctly is the challenge when it comes to medical image registration. But as far as rigid body registration is concerned, or rigid transformation are concerned, well studied subject. A lot of softwares exist. The errors are known, etc. So you are welcome to try these out in your projects. Okay, so the next transformation that we will see is the so-called affine transform. So what affine transforms do is to preserve collinearity, right? So if there are 3 points that are collinear in the input space, that is your input image, it's a fixed image, there are 3 points which are collinear, then after applying this transform, it still remain collinear, right? So that is the only guarantee behind this transform. This is the general expression for the transformation, x prime equal to a x plus t, where n is a n-dimensional square matrix and t is an n-dimensional vector, and this is the translational vector, one for every dimension of the image. And so the parameters are basically n cross n coefficients, or capital N, okay, n cross n coefficients of the A plus the n components of the vector t, right? See the affine transform does both some shearing as well as skew of the image, okay, and Of course, optimization is always a problem, but typically this is another general transform that you would use in the context of even rigid registration. Okay, Affine transforms are used, but of course the simplest rigid registration transform is the rotation and translation model. Okay, so that's typically the rigid body model that you would use first. That's the first step. And slightly more complicated is this model where you can use the affine transform. Correct. So you first start off with the rigid body model where you only have rotation and translation, and then you should slowly progress to this one. In fact, even scaling makes the problem more complicated. But like I said before, rigid body registration is well studied, so typically that would be a very good place to start. Okay, so these are the simplest transformations that you can use when you are trying to do rigid registration. And there are, like I said, software packages available which perform this kind of registration, and welcome to try those. I'll give you a summary of that when we go to the next week, where we also look at non-rigid registration. Thank you.